Hi, my name is Dear Tiagi, and in this video, I'll be going over how particle accelerators work and why we even use them. So to start, what does a particle accelerator actually do? Well, it's in the name. A particle accelerator accelerates charged particles like electrons and protons to high speeds. These high speeds usually near the speed of light, especially at these bigger facilities. And so why do we even accelerate these particles to these high speeds? Well, the main reason why is we want to collide them. We either want to collide them or we want to target them to certain areas or certain things. And so what happens is when we collide these particles together, a lot of things can happen when we collide them together. For example, we could release energy, or we could have a nuclear reaction between them, or we could scatter particles, or even create new particles. So the reason why we use particle accelerators are to, speed these particles up and then collide them or target them to a certain area. And then these things happen as a result. But what are the actual fields where we use these accelerators? Well, the main field, and you guys might know about this field, is with physics research. So with physics, particle accelerators are useful because, number one, they can help us understand new particles, discover them, like the Higgs boson. So the Higgs boson was a new particle that was discovered, new subatomic super tiny particle that was discovered by CERN at the Large Hadron Collider, which is a huge collider, the biggest particle accelerator in the world, in Switzerland. And they discovered this particle, the boson, in 2012. And so that's one reason why these accelerators are useful. Another reason why is because they can help us to study forces and interactions. And being more specific, they can help us understand the standard model of physics, help us test it. And so the standard model is a framework that describes all fundamental particles and all forces, fundamental forces, except gravity. And so by using particle accelerators, we're able to see the interactions and the collisions. It allows us to test the validity and the components of the standard model. And finally, the particle accelerators are useful in physics research because they can help us research Big Bang conditions. Right? And the Big Bang conditions, by researching that, we understand, how our universe formed, where we came from, and that just provides us a lot more knowledge and a lot more things that physicists are interested in. But physics isn't the only, field where particle accelerators are useful or where they're used. We also use particle accelerators in medical applications. So in medical applications, particle accelerators are used to sterilize things in some cases. And the advantage of using a particle accelerator to sterilize something versus using heat or chemicals is that it's less intrusive than heat or chemicals. It's definitely harder for sure, but it is less intrusive, and it doesn't really damage as much as heat or chemicals could. And so one reason they use it, medical field, is to sterilize. They also use it to help in cancer therapy. So the advantage with particle accelerators in cancer therapy is they can use this thing called proton therapy to use protons to directly target tumors and attack them. So they used particle accelerators and they directly target cancer tumors or other bad tumors, and they target it with these protons by firing these rapid protons at them, which eventually kills the tumor while not damaging the cells around it. And so it's one advantage of using particle accelerators in one field. They're also used to create radioisotopes that are necessary for certain radiopharmaceuticals that are used in treatments such as cancer treatment or other kind of treatments that need radiopharmaceuticals. And finally, particle accelerators are useful in industrial applications. So the main example is probably for sterilization, right? So sterilization of components if you need that. And so an example where you need really sterile components and where particle accelerators could be useful is in the semiconductor field, right? Because you need these semiconductors to be very clean, dust-free, and so particle accelerators can help you to sterilize those. And those are some fields. So now I want to discuss how particle accelerators actually work. And before I start, I just want to say that there's many types of particle accelerators, but for this video, I'll be going over the three major ones. And you'll see soon that all the three major particle accelerators are all very similar to each other, and they all, rely on the same fundamental physics principles to operate. So to start, let's start with the linear accelerator. So let me just draw a diagram and I'll explain it after. So diagram. Okay, so with this diagram, the first part we have is the proton emitter, or sorry, the particle emitter. Doesn't have to be necessarily a proton. And what this does, again, it releases a charged particle out of here. Right, so let's imagine it releases a proton. And then here, these are all semiconducting materials, and they're all connected together in alternating format. And from here, we have a voltage applied. Okay, so we apply a voltage, and we're connecting them in alternating fashion. And so what happens when we apply a voltage, a high voltage, we get a charge on each of these materials, and these are called drift tubes. We get a charge on each of these drift tubes. And so let's say this is negative, positive, negative, and this is obviously positive because we shot out a proton. And so just one more thing, these drift tubes are made out of, again, superconducting material. And the superconducting material is used because it's very efficient and it's very good at conducting, voltage and electricity through it, which is why you use the superconducting material. But the issue is, for this material, you need to cool it to very low temperature. And so to cool it, we have these cryogenic systems that are used to cool these tubes, these drift tubes, to very low temperatures, such as, below 1.9 Kelvin, which is about negative 273 or negative 274 degrees Celsius. Okay, so what happens is basically this particle, right, it's positive, and this is a negatively charged tube. And so what happens is you have an RF electric field here, right, is a field that attracts here and here. And so this electric field, it places a force on this charged particle, an electromagnetic force that attracts it into the little drift tube. And then what happens is this accelerates, because again, there's a force being applied because of the electric field that is made from the voltage, and so it pulls that particle into the tube. And then what happens is this tube, the currents change. So we have, connected to this voltage, we have an oscillator, right, this oscillator. And what this oscillator does is it changes the polarity of the voltage. So it just basically switches the direction. And so what happens is when it switches, imagine if the particle's in the middle, this switches to positive, this switches to negative, positive, negative. And so because of this switch, what happens is now there's an electric field going, still going this way, I guess. But now what's going to happen is that's going to be pulling this way, right? The particle is going to be pulled that way because of this electric field. And so the idea is, it's very similar to maglev trains. If you watched my video on that before, maglev trains, they continually switch the magnets to pull the train forward. Similar idea here, we continually switch the voltage, the direction to pull this particle forward using, electric fields and electromagnetic waves. And so again, same idea here, it'll go here, it'll switch, go here, switch, and it keeps accelerating. And so you might notice I made each tube longer, so it's short, medium, and long. And the idea is these tubes will get longer and longer and longer because the way this oscillator works, it just works based on a frequency wave. So it works at like a gigahertz frequency usually. and it changes at a constant rate. So it changes like 1, 2, 3, 4. So constant rate, but the issue is we don't exactly know when it's at the middle, and also it's speeding up, so right? So if it speeds up here, it's not going to be at the same middle when this oscillator changes. So the idea is by making the tubes longer, you can make sure that the frequency, which is constant, lines up so that the particle is always in the middle when the polarity changes. And so that's the idea behind a linear accelerator. Oh, one more thing. Also, this whole system, you can see I draw 2 lines around it. I drew these 2 lines because this whole system is in a vacuum. And this vacuum is pressurized at around 10 to the negative 9 to 10 to the negative 11 torr, which is a very, very low pressure. It's lower than the pressure in space, even. And so the reason why it's such a low pressure is so the particle that's accelerating doesn't hit any gas molecules. Because you can imagine if it hit a gas molecule, it would slow down tremendously, especially if this whole tube was filled with these molecules. So it would slow down if that was true, but luckily we have this vacuum, and so it doesn't slow down. And again, the end product is you have a very fast beam, which is all thanks to the alternating current that is generated by this oscillator that oscillates at a constant frequency. Next, let's look at this another type of particle accelerator called a cyclotron. So a cyclotron is a little different from a linear accelerator, but it works in a little bit of the same way. So a cyclotron, how it works is you have these 2 D-shaped, terminals here and here. And again, these are both hooked up to voltage, and they have an oscillator that oscillates, the frequency. And so we can imagine, let's say we have an electron here, right? And let's say this is positive, negative. So again, the same idea, the electric field is going to pull this electron this way, it's going to accelerate. But the issue is, if we keep doing that, it's just going to stay there, right? And so we don't want it to stay there, we want it to, loop back. And so the idea is, if we apply a magnetic field at this point perpendicular to the 2Ds, so if these are the 2Ds, right, the plane, if we apply a magnetic field perpendicular to that, by the left-hand rule, what's going to happen is there's going to be a force, a EM force, this way, that pulls the particle down, like so. Now, if we change the polarity at this point, when it's being pulled down, so we change the negative positive, like so, what's going to happen is it's going to be pulled back again to this way. And here it's accelerating, but if we do the magnetic field again, it's going to curve, and this time the radius is going to be bigger, because again, it's going at a higher speed, so the radius is obviously going to be bigger because it's going faster. Now we change it again, positive, negative, gets pulled over here. We apply a magnetic field to curve it. It curves, and the process continues, and each time it gets faster because at this point in the middle, between the 2Ds, it's accelerating because again, the magnetic field, the electric field, is producing a force that pulls the particle faster and faster and accelerates it. And so this keeps happening, and it keeps going in this little circle until we have some kind of exit pipe that just shoots out that charged particle that's going really fast. And yeah, those are cyclotrons. And an advantage of those over linear accelerators are that they take up much less space. A linear accelerator, if we want to accelerate it to tremendous speeds, like maybe near the speed of light, we'd have to use hundreds of miles of track to get that particle to accelerate that fast. But with cyclotrons, since they're going in a circle, it requires much less space. But the issue is the radius is changing, and so that might make it tough to design it, and also in terms of speed. And so the last solution we have, the last type of particle accelerator, is this accelerator called synchrotrons. And synchrotrons are very much a combination of the 2 previous particle accelerators we looked at. So synchrotrons, they function a lot like linear accelerators, except the thing is, though, they're in a curve. And a synchrotron is actually what the Large Hadron Collider uses up in Switzerland. And so with a synchrotron, what happens is you have a curved track, and you have these, again, drift tubes that are attached periodically on the track. like so. And again, these drift tubes are, again, have a voltage applied to them, and so they all have an electric field that, again, pulls the particle through this tube and makes it go accelerate through the tube. So the same way linear accelerator works, the same switching happens here, and the same kind of acceleration pattern happens here. But the only change is when the particle goes here, so with the linear accelerator, the particle will just go straight like so. In this case, the particle wants to go straight, it wants to keep going forward, but the issue is we can't make it keep going forward, we have to turn it, curve it. And so applying the same principle we used for the cyclotron, in this case, when it's in between a drift tube, like so, what we do is we apply a magnetic field or magnetic force here, perpendicular again to the plane, and what happens is it's going to curve down and it'll go in a circle. So every time it's on a drift tube, so here, 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 etc., we apply a magnetic field, the particle curves based on the field, and it goes through, in the circle pattern. And again, each time we're accelerating it using these drift tubes that are electrically charged. And the thing is, though, we also have to increase the magnetic strength of the field whenever we, go through a cycle, because you can imagine as the particle goes faster, we need more of a magnetic force to keep it in a circle. And so the oscillator that we use has to be super, super duper, synchronized and, really, really synchronized. I guess another way of saying it, with the particle's motion and the electric field and the magnetic field, which I guess is why they call it, synchrotrons, because they have to be super, super synchronized with the charged particle. One more thing, all these systems, these accelerators, they all have these things called quadruple magnets. And quadruple magnets, a way you can think of them is you can think of them like a lens. So if you imagine the sun, to focus that, light from the sun, you might use like a lens to focus it in. So the same way here, to focus a charged particle or beam, a way people do that is through quadruple magnets. And so how a quadruple magnet works is you take a magnet, 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 and a magnet, so north, north, south, south, and you put the beam through that, so the beam goes here. What happens is that beam is going to be more focused and more directed because you apply these magnets in this format, because there's a field around it that produces a more concentrated beam and more focused beam in that direction. And finally, of course, at the actual particle accelerators, you have these control systems and sensors that monitor the system by a closed feedback loop and ensure that it's all working properly and ensures that the particle is actually accelerating. And yeah, those are how particle accelerators work, and that's some of the use cases. Thank you all for watching, and I'll see you guys all tomorrow. Bye.